Hi students, welcome to Max Point of View. Today we are going to solve each and every theory question from the chapter Radioactivity Part B, that is nuclear fission and nuclear fusion. Along with this one we have only two numericals, that is also we are going to cover in this video only. But before solving this any questions, my suggestion is watch the concept video, because once you watch the concept video you will get some knowledge. Once you get that knowledge, if you come back to this video, okay, then you will get some idea what kind of questions they are going to ask. Then along with me you can also solve few questions. So without wasting any time, we'll start with our first question. All these videos are available in the description box. Our first question, see, when you see this question you will get confused. See, we just have to complete the values, but if you are seeing this as a difficult question, this is a very easiest question, because you don't have to by heart anything. If they are asking this as an example, then you have to by heart the complete equations. They have given the equations, we just have to complete it. I will teach you the method how to complete it in an easier way. You don't have to by heart anything. Listen. The first thing you need to know is, whenever it comes to nuclear fission or nuclear fusion, the atomic number, the down part is atomic number and the above part is mass number. Both are conserved. What do you mean by conserved? That means how many mass numbers are here? 235 plus 1, 236. When you add all the mass numbers, you will get 236 only. You will get 236 only. Now, how many atomic numbers are here? 92 plus 0, 92. So, when you add all the atomic numbers, you will get 92 only. This is nothing but this one. Atomic numbers and mass numbers are conserved in a reaction. Now, you got it right. Now, with that concept, aramsa we can solve it. You don't have to by heart anything. Listen, 235 plus 1. So, complete in A. Okay, the mass number symbol is 236 and atomic number is 92. You don't have to do all these things in the exam. Just like that you can do. For your reference I am writing this one. Now see here. So 235 and this one 92. See how many neutrons are there? 3 neutrons. That means 3 into 1, that will be 3. 3 into 1, that will be 3. The complete mass number here only for this neutron will be 3. So 3 plus 92, that will be 95. So this side we have 95. Okay, so how much we have to add here? Complete was 236. Okay, now we had 95. How we got 95? 92 here, 1 here, 1 into 3, because we have 3 neutrons. 1 into 3, that becomes 3. 3 plus 92, 95 we have. So the remaining will be 141. 141. That's it. This is how you can calculate. So when you add all these things, see, when you add this one and 3 into 1, you should get the complete mass number, that is nothing but 236. Next we'll go for this one. 92 is the atomic number. Here 92 plus 0, the complete the atomic number on the LHS is 92. When you add on the RHS, you should get 92 only. See, when it comes to neutron, it is 0. 3 into 0, again it is 0. Now we have 56, and here if I write 36, 36 plus 56 will get 92. That's it. This is how you can complete the diagrams. In the same way, we are going to complete this one also. So for B, this one, atomic mass number 235 plus 1, again it is 236. A is 236 and Z will be 92 plus 0, 92. Okay, when we add these two, okay, see, we know when it comes to neutron, okay, in a nuclear fission reaction, 3 neutrons will be released. Keep that in mind. This is a nuclear fission reaction. So that is what we have learnt in concept video. In a nuclear fission reaction, 3 neutrons will be released. So we'll write 3 here. If you write 3, okay, now see, 148 plus 85 plus 3 will get 236. We'll get 236. Now the mass numbers are done. Now we'll go for the atomic number. Atomic number is 92. See, here we have 35. 3 into 0 is 0. So 35 plus some value, you should get 92. That is nothing but 57. That's it. So this is how you solve the complete the reactions. You should know mass number and this one atomic numbers are conserved. That means whatever the complete mass number we have on LHS, that should be equal to the complete mass numbers on RHS. That's it. Now we'll solve our second question. See, second question also it's based on equation. Now this is based on fusion reaction. We have to complete the fusion reaction equation. This is very simple compared to fission reactions because the number is very simple. Listen, the same way atomic mass numbers are conserved, atomic numbers are also conserved. And one thing you should know, whenever, see, this is a hydrogen, this is helium, this is hydrogen. Whenever, see, this is not a stable hydrogen. This is not a stable hydrogen. What do you mean by unstable hydrogen? That means, see, the stable hydrogen value is this one. Okay, atomic number is equal to the mass number. If that is not equal, that means it is a unstable hydrogen. When this happens, we'll get the stable hydrogen. This is one point. Then we know in the first fission reaction we learned neutron value will be 1 by 0. Correct, 1 and 0, that you should know. So once this unstable hydrogen undergoes fusion reaction, it becomes stable. And we know neutron, the value of neutron will be 1 and 0. If you know this much, you can aramse solve these questions. Listen, whenever these kind of questions, that too based on fusion reaction is given, first don't go for helium. Why? Because whatever after substituting the value of hydrogen, whatever the remaining value is there, that is what we are going to write it here. Okay, now listen, what is the number of mass numbers? 3 plus 2, that is 5. Correct. And we know for hydrogen it is always 1:1 and 1. So 1 here. So if 1 is done, how much is remaining out of 5? That is 4. That's it. Next one, we'll go for here. So what is this one? Mass number 2 plus 2, that is 4. We know here it is 1 and the remaining thing will be 3. See, 2 plus 2 is 4. 1 is already done. Okay, that is printed in the question. If 1 is done, the remaining thing will be 3. So 3 plus 1, again it is 4. Now we'll go for this one. Okay, atomic numbers. 1 plus 1, that is 2. 2 is already here, and we know for neutron it is always 0. If you get 0, that is perfect. So this is how you solve the fusion reactions. Our next question, name the process nuclear fission or nuclear fusion in which energy released per unit mass is more. Here the important word is unit mass. So we have one more question, we'll go for it later. See, first question, listen. We know, if you have seen the concept video, we can aramse say answer is nuclear fission. Correct? No, that is completely wrong. We know in nuclear fission reaction energy will be 190 mega electron volt. That is compared to nuclear fusion, that is huge. In nuclear fusion we are getting only less energy compared to nuclear fission. But they are asking in the question, they have specified one word, that is per unit mass. Per unit mass, whenever they mention per unit mass, the answer will be nuclear fusion. Keep that in mind. Nuclear fusion. Okay, if the word per unit mass is not there, then the answer would have been nuclear fission. Then, second question, name the process fission or fusion which is possible at ordinary temperature. In the concept video itself we have learnt, so at an ordinary temperature only nuclear fission is possible. So these are the facts you should know. Nuclear fission. Our next question, what is the source of energy of sun or stars? See, in the concept video we have learnt, but here they are specifically asking what is the source. That's it, you don't have to write the stories. Answer is nuclear fusion. Answer is nuclear fusion. See, they are not asking you to explain how the nuclear fusion happens inside a sun or star, correct? They are just asking what is the source of energy of sun or stars nuclear fusion. That's it. If they are asking you to explain, then go for the explanation. Don't write something extra and lose marks. Write the precise answer. That's it. This is the this one, source for sun or stars. That's it. Our next question, listen, they have given two equations. We have to identify which is nuclear fusion and which is nuclear fission. Our answer you can identify with many hints. Listen, when the uranium comes, it is related to nuclear fission. Keep that in mind. So in the first question only we have understood. See what the difference between first and second question of this part. Okay, will tell you everything. This is nuclear fission and nuclear fusion. So see, whenever uranium comes, that is nuclear fission. Nuclear fission. When the hydrogen or helium comes, okay, at the this one product side, that is nuclear fusion. There is one more way to identify, very easiest way. The numbers, okay, numbers will tell you if you are calculating in nuclear fusion, okay, the numbers in nuclear fusion will be always less than 10. Keep that in mind. Nuclear fusion, the numbers are always less than 10. If it is more than 10, definitely it is nuclear fission. So A is nuclear fission and B is nuclear fusion. So this is how you identify the equations. Our next question, what do you mean by the nuclear energy and what is responsible for its release? Very simple question. Listen, the energy released by the nucleus during the nuclear reaction, that is nothing but nuclear energy. You got my point? The energy released by the nucleus during the nuclear reactions, that is nothing but nuclear energy, and they are asking what is the responsible for its release. The responsible release of nuclear energy is nothing but nuclear fission and nuclear fusion. Our next question, write down the Einstein's mass energy equivalence relation. Explain the meaning of each symbol used in it. Very simple. Listen, the equation they are looking for is E is equal to, actually we know that is E is equal to mc square, correct? But when it comes to Einstein mass energy equivalence relation, that too in this chapter, that is delta m c square. Delta m c square. Here he represents energy in joules. Delta m represents loss of mass. A loss of mass in terms of kg, and c we already know that is the speed of light, that is nothing but 3 into 10 power 8 meter per second. That's it. Our next question, what is AMU? Express 1 AMU in mega electron volt. MEV means mega. Mega means 10 power 6. Electron volt is nothing but 1 unit of energy. One more unit of energy. Don't worry about it. First we'll learn about what is AMU. AMU is nothing but, listen, AMU is nothing but the mass of atomic particle. Atomic particle, okay, is expressed in terms of AMU. What is AMU? Atomic mass unit. And they are also asking express 1 AMU in mega electron volt. 1 AMU is equal to 931 mega electron volt. That's it. Now we have one more question. Write the approximate mass of proton, neutron and electron in AMU. See, these kind of questions, where you can remember the values, those kind of questions will not be asked in board exam, but for your reference I am going to give the answers here. Our next question, what is nuclear fission? Name the particle used for it or name the substance used for it. Write one fission reaction. Very simple question. This is what we have learnt in concept video. Listen, what do you mean by nuclear fission? The process in which heavy nucleus split into two nuclei of nearly the same size when bombarded with the slow neutron to release the tremendous amount of energy. And what is the substance used for it? That is nothing but, see, we are using, in this equation we are using the uranium. Uranium is the substance used for it, and this is the equation they are looking for. This is what we have learned in the first question of this video. Our next question, write the approximate value of energy released in the fission of one nucleus of uranium 235 92. What is the reason for it? This is what we have learned in concept video. Listen, very simple. How much amount is released? Amount of energy is released 190 mega electron volt. This much energy will be released. This is huge, we cannot even imagine. Okay, and they are asking the reason for release of this much of energy. Very simple, the loss of mass on the product side is the main cause of release of this much of energy. Question number 6, 7 and 8, these are the questions. These questions we have learnt in the concept video, and there is no bit change in the questions. That's why we are going to skip it. All these things we have learnt in depth. They are asking for 2 uses, we have learnt many uses. They are asking for few differences, we have learnt many differences, and the chain reaction and how it can be controlled. All these things we have learnt in depth in the concept video. That's why, anyhow, there is no change in the question. That's why we are going to skip this one. All these concept videos, whatever I am talking about, all these things will be in the description box. You can watch it and learn it. Our next question, what is nuclear fusion? Give an example and write the reaction. Very simple. See, first we'll understand what is nuclear fusion. Nuclear fusion is a process in which where two lighter nuclei combine to form a heavy nuclei along with the huge amount of energy is released. This is the definition of nuclear fusion reaction, and they are asking for an example. Hydrogen and hydrogen, okay, atoms fuse to form a helium. This is an example. And next they are asking for one equation. This is the equation or a reaction. This is the reaction they are looking for, and they are asking one more question. What other name is given to nuclear fusion and give reason? Very simple. What is another name for nuclear fusion? That is what we have learnt in concept video, right? What is another name? Thermonuclear fusion reaction. Thermonuclear fusion reaction, and they are asking reason for also. Very simple. Why? Because it happens, this one, nuclear fusion reaction happens at a very high temperature. That's why it is also called as thermonuclear fusion reaction or thermonuclear reaction. Our next question, why is a very high temperature required for a process of nuclear fusion? State the approximate temperature required. Very simple question. This is what we have discussed in concept video. Listen, we will discuss here also. First, to answer these kind of questions, we need some basics. See, whenever we are talking about nucleus, okay, we are talking about nuclei. What do you mean by nuclei? More than one nucleus is called nuclei, correct? When two nuclei are approaching, both the nuclei are made up of positive charge, correct? Because in the nucleus, what we have? Protons and neutrons. Neutrons are uncharged, but protons are positively charged. When the two nuclei are approaching, okay, because of the positive charge, they'll repel. Positive charges, what happens? Two positive charge repel, one positive, one negative attracts. But here we are talking about only nuclei. That's why both have positive charge. They'll start repelling each other. That the repulsion is nothing but electrostatic repulsion. Now this is the basics. Now we'll understand how to write the answer in the exam. Now, when two nuclei are approaching each other, due to their positive charge, the electrostatic force between them keep on increasing. The electrostatic force of repulsion becomes too strong between them to fuse. Too strong, the repulsion becomes too strong, so that they cannot fuse. That's why at ordinary temperature it is not possible. Not only ordinary temperature, this question can be asked in different way. Okay, why it is not possible in ordinary pressure also? For both the question, a very high temperature and very high pressure, the answer remains same. So at ordinary temperature and pressure, to fuse the positive nuclei, it is not possible. So it requires high temperature. To fuse them. And also they are asking for the approximate temperature required. That is nothing but 10⁻⁷ Kelvin. 10 power 7 Kelvin. This is very huge, correct? 10 power 7 Kelvin. That means almost 1 crore Kelvin. 1 crore Kelvin temperature is required, and also the approximate pressure. So in this question they are only talking about temperature. This is the value we require. Our next question. Write one nuclear fusion reaction. This we have learnt already. That's why I have written already. Next. State the approximate value of energy released in the reaction mentioned in part A. This is part A, right? So in part B they are asking energy released in part A, that is nothing but 3.3 approximate. They are asking 3.3 mega electron volt. This is what they have given in the textbook. This is enough. For different equations, different energy will be released. Whatever the equations you have writing, okay, you are writing the same related to that only energy you have to write. You should not write some other energy for some other equations. You have to see what equations you are writing, but based for that equation what is the energy required. All these things we have learnt in the concept video, and that is what they have given in the textbook. Listen. Next we will go for the C sub question. Give reason for the release of energy stated in part B. See, this one we have learnt in another question also, correct? I already learnt. That's very simple answer. The loss of mass of a substance. The loss of mass of a substance on a product side is the main cause for the energy released. That's it. Our next question. State one similarity in the process of nuclear fission and fusion. State two differences, and they are asking for some examples. All these things we have learnt in concept video. That's why we are going to skip it. But one question. State one similarity in the process of nuclear fission and fusion. This is very important question. That's why I am going to give you the answer. Very simple. What is the similarity between fusion and fission? There will be a loss of mass on the product side in both fusion and fission reaction. This one you can write, or else. So this one, the energy released, there will be energy released by both the reactions, nuclear fission and nuclear fusion. Out of these two you can write any one to get full marks. Our next question. Name two isotopes of uranium which are fissionable. Very simple. Uranium-235 92 and uranium-238 92. So this question is very important because apart from this example there are few sub questions, those are very important. Then we will go for sub question B. Which of the isotope mentioned in part A above is easily fissionable? Give reason. See, easily fissionable, the answer is uranium-235 92. Why? Because this is fissionable. This is uranium-235. Okay, don't write this. This is the answer because uranium-235 92 is fissionable even with slow moving neutron. Even with slow moving neutron. It is also possible with fast moving neutron, but uranium-238 92 only fissionable with fast moving neutrons. See, uranium-235 92 can be fissionable along with slow moving neutrons also, as well as fast moving. But this one, uranium-238 92 only fissionable with the fast moving neutrons. That's it. So only fissionable. This is very much important. Then we'll go for question C. State whether the neutron needed for a fission reaction of an isotope mentioned in part B, okay, part B above is slow or fast. See, we are using both the isotopes, correct? Both the isotopes. We need both slow and fast. Slow for uranium, for uranium-235 92, slow for uranium-238 92, we need fast. So the answer for this question, sub questions be both slow and fast. That's it. Now we'll start with our numericals. There are only two numericals. We'll go for the first numerical. In fission of one uranium-235 nucleus, the loss of mass is 0.2 AMU. Calculate the energy released. See, they have given the data. First we'll write it. See, first question. Okay, here loss of mass. Okay, that is nothing but delta M, that is 0.2 AMU, and we know 1 AMU is equal to 931 mega electron volt. Okay, this is the value of the energy, correct? So what energy? Light energy. So what is we have to calculate? E. Now E is equal to delta M C square, correct? Delta M C square. When the value of AMU is given, we don't have to use C square. So the answer will be 0.2 into what is 1 AMU, that is 931 mega electron volt. So answer will be 186.2 mega electron volt. This is the answer we are looking for. That's it. Our next question. When 4 hydrogen nuclei combine to form helium nucleus in the interior of sun, the loss of mass is 0.0265 AMU. How much energy is released? The similar question we have done in first question, right? The same thing here they have given in different sentence. So question number 2, whatever the hydrogen they have used to form a helium, that is done. Loss of mass is equal to 0.0265 AMU. When AMU is given, the energy formula will be delta M, okay, in terms of AMU, correct? This is enough. AMU means atomic mass unit, keep that in mind. So that is nothing but 0. We know 1 AMU, okay, 1 AMU is equal to 931 mega electron volt. So E is equal to 0.0265 into 931 mega electron volt. Answer will be 24.63 mega electron volt. Why the energy is less? Why? Because in sun they are talking about, in the sun nuclear fusion, whenever the fusion happens, the energy release will be less compared to fission reaction. That's it. So now we have completed all the theory question as well as numericals. First always go for the concept video, then theory, and for the numericals, then you will understand everything. Thank you.